use, if we set a equal to minus 1 by 3 into 2 by 3 and b equal to 1 by 3 into 2 by 3 for the Urizen's lemma. Okay? So by Urizen's lemma, now we apply Urizen's lemma because a1 and b1 they are disjoint and closure subsets of x. So we can apply Urizen's lemma here. By Urizen's lemma, by Urizen's lemma, there exists a continuous function. There exists a continuous function. So let's denote that continuous function by G2. There exists a continuous function. So G2 or yes, first it was G0. Now we define G1. There is a continuous function G1 from x to the interval. We choose the interval here minus 1 by 3 into 2 by 3 and 1 by 3 into 2 by 3. That's the closed interval. Okay, such that this G1 it maps each point of a1 onto minus 1 by 3 into 2 by 3 and each point of b1 onto 1 by 3 into 2 by 3. Each point of b1. Now we define f2. Now define f2. Define f2, which we define by f1 minus g1. First, what's f1 here? F1. When we have defined f1 is equal to f0 minus g0. Now we define f2, which is equal to f1 minus g1. So, but f1 is f0 minus g0. It's equal to f0 minus g0 minus g1. So that's equal to f0 minus times g0 plus g1. So that's f2. That's f2. Then f2 is continuous. Then this f2, it's a function from x to the interval minus 1 plus 1 is continuous. Is continuous. And as in the previous case, we have shown that mod of f1x is less or equal to 2 by 3. So, but here we will show that mod of f2x is less or equal to 2 by 3 whole square. So, and then this and mod of f2x is less or equal to 2 by 3 whole square. It's less or equal to 2 by 3 whole square. So this again verify. You verify this one. As in case in the previous case, we have taken 3 cases there. One when x is in a0, second when x is in b0, and third when x is neither in a0 nor in b0. And here we take we again take 3 cases. First case x is in a1, because here the sets are a1 and b1, and second case x is in b1, and third case x is neither in a1 nor in b1. And you can easily do this. This f2 of x is less or equal to 2 by 3 whole square. It's less or equal to 2 by 3 whole square. Okay. So this is simple. It's not too difficult. You can easily do this. Or you can see the detail is from my lecture notes. Okay. So that's this is simple. This one is simple. And what's mod of g1x? You can see this mod of what's mod of g, and also this mod of g1x is here. Mod of g1x is here. So the values lies between minus 1 by 3, 2 by 3. It's less or equal to 1 by 3 into 2 by 3. It's less or equal to 1 by 3 into 2 by 3. The next we have 2 by 3 square. So in next step we choose a is equal to minus 1 by 3 into 2 by 3 whole square for this Urizen's lemma, and b is equal to 1 by 3 into 2 by 3 whole square. So then the function mod of g2x will be less or equal to 1 by 3 into 2 by 3 square. So we continue this process n times. We get a sequence. Continue this process indefinitely, not n times. So continue this process. We get a sequence. Continue this process. We get a sequence. We get a sequence g0, g1, so on. and the second sequence is f0, f1, f2, so on and so forth, such that these g naughts, these gns, they are the functions from x to the interval -1 to 1, and f naughts are the functions from f to -1 to 1. Now gns are not functions from 1 to 1. Gn is a function from -1/3 into 2/3 power n, and this one is 1/3 into 2/3 power n. So it's this interval. This gn is a function from x to -1/3 2/3 power n, 1/3 2/3 whole power n here. What's g1? g1 is a function from -1/3 times 2/3, 1/3 times 2/3. So g1. So g2 will be -1/3 2/3 whole square, 1/3 2/3 whole square. So in general gn will be -1/3 2/3 whole power n, 1/3 2/3 whole power n. Okay. It's a function from x to -1/3 2/3 whole power n, 1/3 2/3 whole power. That's the interval. And f naught is a function from f to -1 to +1. And this mod of gn x, it's less or equal to 1/3 into 2/3 power n, and mod of fn x, mod of fn x is less or equal to 2/3 power n, 2/3 power, and mod of f1 x is less or equal to 2/3, mod of f2 x is less or equal to 2/3 whole square, and so on. Now with this condition, they are connected, these gns and fn, they are connected by this following relation: fn is equal to f0 minus g0 plus g1 plus 1 plus up to gn minus 1. Like f1 is equal to f0 minus g0, f2 is equal to f0 minus g0 plus g1. So let me, this f2 is equal to f0 minus g0 plus g1, f2 is equal to f0 minus g0 plus g1. So in general, fn is equal to f0 minus g0 minus times g0 plus g1 plus 1 up to gn minus 1. That's your fn and g. So now let's denote this sum Sn. It's a partial sum of this one, and a partial sum. It's equal to g0 plus g1 plus 1 plus gn. Then you can see that this mod of gn is less or equal to then series n runs from 0 to infinity. This gn of x. What's gn of x? It's less or equal to 1/3 times it's less or equal to 1/3 times series 2/3 whole power n, because each gn is less or equal to 2/3 whole power n, 1/3 times, and that sum is equal to 1. It's equal to, this is 1/3, and this sum, this series n runs from 0 to infinity, it's equal to 3/1. That series, sum of series, and this is 1/3 times 2/3, it's equal to 1. So that means this the series is convergent, which means Sn converges uniformly. So therefore Sn converges uniformly on x, to f function, to a bounded continuum, because each gn is continuous and bounded function, therefore, and that space is a complete space actually. So it converges uniformly on x to a bounded continuous function, let's denote that by f dash from x to -1 to +1. So what are these gns? Okay, for these gns, it's g1. So their function is from x to -1 to 1. Actually they are not the function from minus, since gn is a function from x to -1/3 2/3 whole power n minus 1/3, so it's actually subset of -1 to +1. So I can treat this gn as a function from x to -1 to +1. I can treat this as a function from x to -1 to +1. This can be, so this f dash, it's a limit of that series. Each g0 is a function from x to 0 1. So therefore their limit, the limit of this series will be a function from x2 minus 1 2 plus 1, and it's a continuous function because the convergence is uniform here. It's a continuous function, so that f dash is a continuous function. F dash is a continuous function. So, and we show that this f dash is actually extension. This f dash is actually the extension. So for this we have a this is a fn. What's fn actually? Fn is equal to f naught minus g naught plus g1 plus so on plus gn. So that means fn is equal to f naught minus sn. Now let's name it a star. Now what's mod of fnx? It's less or equal to 2 by 3 whole power n, letting n approaching to infinity. It will be approach to 0 because 2 by 3 is less than 1. 2 by 3 is less than 1. So letting apply limit here in this case, therefore star gives 0 is equal to f naught minus f dash. F naught minus f dash. So which implies f naught is equal to f dash, but what's f naught actually? F naught is f actually. F is equal to f dash on f. So thus f dash is an extension. Thus f dash is an extension of f. Extension of f from f to whole space. F to whole space x. It's a continuous. You can say it's a continuous extension. Is a continuous extension of function f from the closest subspace f to the whole space x. So that's our Tietz extension theorem. That was our Tietz extension theorem. That completes the proof of Tietz extension theorem. So you can easily prove its general part now. That's not too difficult. So next we have Urizen's embedding theorem. Urizen's embedding theorem. Before discussing this theorem, I will first discuss one of the important matrix space here that we will use in this theorem. That matrix spaces are infinity. So let's denote this way. Let R infinity is equal to the set of infinite tuples with each component belongs to for all I greater or equal to 1. Okay, let's define this set of infinite tuples. Now we define a matrix on R infinity. This is not whole, but such that and summation mod of xi square I runs from 1 to infinity is finite. Is finite. So it's a set of the infinite tuples, but the infinite tuples has the following properties. Having the following properties, those infinite tuples, the series I runs from 1 to infinity mod of xi square is less than infinity. So they are actually sequences. They are actually this is actually same as you can say it's same as L2 now. Actually, L2 space. Next, as in case of L2 space, it's a set of this. It's a set L2. What's L2 actually? L2 is actually it's a set of sequences, collection of sequences with which are whose square series is finite. So in general, we have actually LP. So what is that LP? Just PF power summable sequences. So it is here square power summable sequences, actually square summable sequences. You can see square summable sequences. So that's our R infinity. So let's define the matrix. Define D. So let's note this by X. Define D from X cross X to R by distance between X and Y, where X and Y they are infinite tuples. It's equal to summation and runs from 1 to infinity mod of X n minus Y whole square whole power 1 by 2. Whole power 1 by 2. What's X? X is an infinite tuple Xn. Y is an infinite tuple Yn. Okay. x is an infinite tuple xn and y is an infinite tuple yn here. So then this D is a metric on X. It's a metric on X. You can easily verify. It's a metric on X. It's a metric on X. This D, this X, R infinity, it's a metric space now, is separable. It has a countable Dana subset. If I take the set Q infinity, which is the set of infinite tuples with each entry is a rational number, and satisfying this property also, then that's a subset of R infinity, and that set is dense in R infinity, and that set is also countable. So it's separable. It's separable space. R infinity is separable, and every separable space is second countable, and therefore second countable, and therefore second countable space. Second countable space, because every separable matrix space is a second countable space. So thus every subset of R infinity is also second countable. Thus every subset of R infinity is second countable. Second countable. So this R infinity we are going to use in Urizen's embedding theorem. So what's actually Urizen's embedding theorem? So this we know that every topological space is not matrixable. It's not matrixable. Every topological space is not matrixable. A matrixable topological, by a matrixable topological space we mean a topological space X is a matrixable if there is a matrix T on X such that the open sets generated by the matrix T coincide with the initial topology which is already on X, because X is already given a topological, so it has certain topology. Then there should exist some matrix on X such that the topology generated by that matrix should coincide with the topology, with the given topology. Then in that case we can say X is a matrixable, and we know that every topological space need not be matrixable because there are topological spaces which are not second countable. That we have already discussed. There are topological spaces which are not second countable, and we know that every matrix space is second countable. Therefore, every topological space need not be matrixable. But here is a theorem, that's Urizen's embedding theorem. It states that if we have a normal space and it is also a second countable, then that topological space is always matrixable. In fact, that topological space is actually a subspace of certain subspace of R infinity, because R infinity is a matrix space, so its subspaces are also matrix spaces as well. And we show that every normal space and second countable, every normal and second countable space is actually a subset of R infinity, which is a matrix. It is actually homeomorphic to subset of R infinity. So in other words, we can say every normal and second countable space is matrixable. That we'll prove in the next lecture. Thank you.